Well, hello, everybody. It's 1 minute past the hour, so I think we will go ahead and get started. Welcome to the inaugural edition of DFI's What's Shaking webinar. My name is John Sinnreich with GRL Engineers. I'm currently the chair of the DFI Seismic and Lateral Loads Committee, and it's my pleasure this afternoon to moderate this session for you. We have a couple of quick rules. During the webinar, all attendees will be muted. There will be a Q&A session following the second presentation. If you have questions during either of the two presentations, please type them into the question box, and I will then go through them with the presenters at the end of the sessions and try to answer all of your questions. So it's my pleasure today to introduce our two speakers, Dr. Arash Khosravifar from Portland State University. His presentation is titled Design of Pile Foundations, Subject to Combined Effects of Superstructure, Inertial Loads, and Liquefaction-Induced Lateral Ground Deformations, as well as Dr. Ramin Motamed of University of Nevada, Reno. His presentation is titled Assessment of Helical Piles in Mitigating Liquefaction-Induced Shallow Foundation Settlements Using Shake Table Testing. So without further ado, I'll turn it over to Dr. Khosravifar.
Thank you, John, and good morning, everyone. A project that we've been working on at Portland State University on design of pile foundations subjected to combined effects of superstructure inertia and liquefaction-induced lateral spreading. A little background about the project. What I'll be presenting to you today is based on the results of a series of projects that were sponsored and supported by DFI, with significant contribution from the members of the Seismic and Lateral Loads Committee, as well as the Drill Shafts Committee. And I want to acknowledge the project advisory members that have contributed to this project over the years: Zia Zafir, Koabina Furiawua, Ann Lemnitzer, Ben Turner, Paul Axtell, Dan Brown, and Azadeh Bozorgzadeh. We also collaborated with industry partners who shared the centrifuge test data that I'll be talking about. Steve Dickinson, Nathan McCullough, and Scott Schlechter, and working with these practitioners helped to ensure that whatever we recommend is practice-oriented and reflects the way these type of analysis is done in practice. The results are from the significant amount of work that our graduate students have done on this project. Jonathan Nasser, Milad Suri, and Thomas Torkelson, and I'll be presenting those results here. We also received financial support from the National Science Foundation. So there are a lot of case histories that document the failure of bridge foundations due to lateral spreading. This is an example of the Showa Bridge in 1964 Niigata earthquake, where liquefaction-induced lateral spreading resulted in excessive deformations in the bridge pile foundations. And that resulted in large deformations at deck and resulted in eventual collapse of the deck. But there are also examples where the piles perform satisfactorily. This is the example, a case study documented by Professor Finn from the 1983 earthquake in Japan, where, as you can see, the approach embankment was completely demolished as a result of the lateral spreading. However, the piles appear to survive and perform satisfactorily, as well as the bridge deck. Here's another good example. So these are based on a case study that was documented by Ben Turner, Scott Brandenburg, and John Stewart on two adjacent bridges in Mexico that were subjected to the 2010 magnitude 7.2 El Mayor earthquake. The left bridge is the highway bridge that survived the lateral shredding. The bridge on the right is the railroad bridge that completely collapsed. The lateral spreading displacement in this case was up to 4.6, so significant amount of lateral spreading, 4.6 meters. And so when you have liquefaction issues in projects, one approach would be, or the first approach would be trying to see if you can design the piles to be able to sustain that load, similar to the bridge example on the left side. If you can't design the piles to be able to sustain the lateral spreading loads, then the next option would be, adopting a more costly ground improvement methods to mitigate liquefaction risk. So what I'll be focusing on in this presentation is on the first approach, how to design the piles and evaluate the performance of the pile foundations when you have liquefaction and lateral spreading issues. More specifically, I'll be focusing on how to combine inertial load from the superstructure mass, so mass times acceleration gives you the inertial load, combined with the lateral spreading loads or kinematic loads from lateral spreading. As you see in the next slide, there's no consensus in design codes and standards on whether if we should combine these two loads or in design, and if we should, what load combination factors we should use. And there are a lot of design questions on this issue: how to estimate the inertial load, how to account for the effect of liquefaction on inertia, how to estimate these lateral spreading loads, and then how to combine them. But I'll be focusing on two specific, I'll address two specific questions. Are these load combination factors affected by ground motion duration? And are they affected by soil profile? So these are the two things that I'll cover in my presentation. So here is a summary of design guidelines on this issue. You see examples of surface transportation, highway bridges, design codes, and also marine transportation agencies on design of ports and wharfs. The MCER ATC 2003 design guideline was one of the first documents that addressed this issue. Oops, sorry. Let me go back. They recommended for independent effect of inertia and lateral spreading, although they did mention that for large magnitude and long duration earthquakes, the two loads may interact. The current AASHTO LRFD does not recommend combining the loads. It does mention that simultaneous effect of the two loads may be considered only for large magnitude earthquakes, magnitudes greater than 8. And I'll be talking about this just in a little bit. The Ashford et al., or the so-called peer report, recommended combining 100% kinematic with 64 to 85% of inertial load. CalTranslator adopted a simplified version of that with the 100% kinematic plus 50% of inertia. The same load factors have been also adopted by Oregon DOT, and I've been told that it's been proposed to be adopted by the British Columbia supplement to the Canadian Highway Bridge Design Code. Washington DOT takes a slightly different approach, which is interesting. They recommend combining 100% of kinematic with 25% of inertia, but they make it dependent on hazard contributions. You would run the deaggregation results. You look at the deaggregation results of your seismic contributions. If magnitudes greater than 7.5 contribute more than 20% of the hazard, then they recommend combining 100% kinematic plus 25% of inertia. For the port and wharf codes and standards, AC61 recommends treating the two loads as independent, so you don't need to combine them. Same recommendation is adopted in Port of Long Beach design criteria. Port of Anchorage, on the other hand, suggests combining full peak inertia with full kinematic load, although they do mention that you can use smaller factors if you adopt to use peer-reviewed 2D nonlinear dynamic analysis, which I'll talk about this in a little bit too. So the bottom line is that there is really no consensus in design codes. The recommendations vary all the way from don't combine the two loads to fully combine the inertia and kinematic loads. And it also appears that these load combination factors are site and project specific. So for bridge foundations or bridge structures compared to wharf and port structures, there appears to be some difference there. So the first project that I'll show you the results of is based on nonlinear dynamic analysis. The second one is based on experimental data from centrifuge test. This shows the schematic of our nonlinear dynamic analysis. It's a 2D analysis in a finite element framework. We use liquefaction constitutive models to model liquefaction of sand. We use fiber section elements to model nonlinear behavior of piles and formation of plastic hinge, and the piles and the soil elements are connected using interface springs. Here is an animation that I think describes the overall performance of the soil and structure. So it's a single bent, intermediate bent with a superstructure mass on top. The soil, the gravity is applied in an angle. So when the middle sand layer liquefies, the top non-liquefiable crust slides down and exerts a load on the pile. That results in permanent deformation in the pile. If I play it one more time, you see the moment curvature behavior at the location of plastic hinge right below the liquefiable layer. You see the soil response on the right side where the contraction and dilative cycles within that liquefied soil, and the pore water pressure reaches to 100% pore pressure ratio, which indicates liquefaction does trigger. So we use these results to back calculate inertia and kinematic factors. And specifically to look at the effect of ground motions, we picked 2 sites in Oregon, one in Portland, one in at Astoria, which is right by the coast, right adjacent to the Cascadia subduction zone. And we selected ground motions based on contributions from shallow crustal faults as well as the Cascadia subduction zone. We developed the target spectra, selected ground motions, and we spectrally matched them and scaled them to the target spectra. That gave us a suite of ground motions with different durations. And you have shallow crustal fault ground motions with short duration, as well as subduction type earthquakes from Tohoku and Mali with much longer duration. And the idea or the hypothesis that we wanted to test was whether if the inertia and kinematic have higher contribution factors when you are dealing with longer duration motions, because they have more time to interact during the motion. So here are the results. On the vertical axis, you see the back calculated inertia multiplier. So we're recommending combining 100% of kinematic load with some percentage of the inertial load. On the horizontal axis, you see the bracketed duration, so D595. The short, crustal motions, shallow crustal motions have typically shorter duration, less than 20 seconds. And then when you get to subduction earthquakes, they have much longer duration. So in the case of Tohoku earthquakes, they get up to 84 seconds. There's quite a bit of scattered data, but if you look at the average value for shallow crustal faults, we back calculated about 60% inertia multiplier. For subduction earthquakes, we calculated 75%. So on average, we see about 15% increase when you're dealing with long duration motions. And this probably supports the approach that the Washington DOT takes. And even though the magnitude of the multipliers that they propose are different than what we found here, but the idea of making the inertia multipliers or the load factors dependent on the hazard contribution appears to be a logical approach in design. The second project that I want to talk about is based on experimental data. So these are recorded data from 5 centrifuge tests that were performed by Steve Dickinson, Nathan McCullen, and Scott Schlechter. When they were at Oregon State University, the tests were performed at the large centrifuge facility at University of California, Davis. This is the large centrifuge with 9-meter radius arm. Here you see on the right an example of one of those models. Here is the bridge, the wharf deck supported on a 3x7 piles. There's a rock dive that these piles penetrate through. Here is the land side, and here's the downslope. These are the cross sections of these 5 tests. So I want to first focus on the top left figure or cross section. This is the first test, NJMO1. These are the 7 piles. The piles are 3x7, so you're looking at the cross section of the piles. 7 piles, they pass through a pretty massive rock dike or rock field, 2 rock fields. And underneath that, there is that liquefiable soil. So this is loose sand with a relative density of 39%. The rock fill liquefies, the loose sand liquefies. The rock fill slides down. So these piles will be subjected to kinematic load from that rock fill, as well as the inertial load from the wharf deck. So that deck has a massive mass that times acceleration provides the inertial load at top of the piles. We use these data to back calculate the inertia and kinematic factors. And if you look at these tests, 3 of them have a pretty similar profile. 2 of them are very different. That really enabled us to look at the effect of soil profile on these load combination factors. One of these tests was completely non-liquefied profile, and while the 3 top cross sections resemble kind of a deep liquefiable soil, this bottom right one is a shallow liquefiable soil with a relatively thin rock fill. Let me show you an animation of one of these test results. These are recorded data. They're not numerical simulation. These are recorded from centrifuge tests. So you see the Loma Prieta earthquake is applied at the base with a PGA of 0.15 G. The wharf deck moves. You can kind of see it's moving during the motion. You can kind of see how the soil profile is responding with those pink cross sections or pink profiles. The maximum soil displacement during this ground motion was 7 centimeters. The maximum deck displacement was 11 centimeters. You see the pore pressure responses on the right. Here is the 100% pore pressure ratio. So you see some of those pore pressure transducers indicate that you do liquefy the soil during the motion, and that results in the rock fill, the liquefaction of the soil, the loose sand, and then the rock fill slides down. So these piles will be subjected to the combined loading. And here are the results. So what I'm presenting to you is the load factors calculated in terms of 100% of kinematic plus X% of inertia. That X is plotted on the vertical axis going from 0 to 1. And these clusters of data are for different centrifuge tests. So this is test 1, test 2, test 3, test 4, and test 5. There are 2 things that you notice when you look at these results. One is that there's some soil profile dependence to these interaction factors. In these first 3 tests, the inertia multiplier varies from, it could be as low as 20% up to 100%. When you look at these 2 tests, the inertia multiplier is much larger. It's close to 100%. So the first thing is that there appears to be some soil profile dependency in these load factors. Also note the 2 dashed line show the range that is recommended by the Boulanger et al. 2007 or the 2011 peer report that ranges between 0.65 to 0.85. The second thing that you notice here, or going back to the first result, what's common between these three tests is a deep liquefiable layer with a massive non-liquefiable rock dike. And what's common with these two profiles is either no liquefaction or pretty shallow liquefiable layer with a thin non-liquefiable crust. The second thing that you notice looking at this figure is that there seems to be some depth dependency to these factors too. So at pile head, the load factors back calculated based on maximum moment at pile head are plotted with those triangles. The circles show the shallow depths, less than 10 times pile diameter, and the squares show the deeper locations, deeper than 10 diameter. So what you see here is that when you're looking at the moments that develop at pile head, you're getting much larger inertia contribution, which is kind of expected because the top of the pile is primarily governed or dominated by the inertial load applied at top of the pile. And when you look at the deeper locations, you get much smaller contribution factors because as you get deeper, the effect of inertia dissipates, and you get much more effect from your lateral spreading. So based on these results, these are our recommended design guideline, which we presented in an ASE paper. So if you're trying to estimate the pile, the bending moments at top of the pile, you only need to apply inertial load. You don't need to combine it with kinematic load. So 100% of inertia, no kinematic, is adequate for estimating bending moments at top of the pile. Now I'm going to jump to this case C. If you're interested in estimating bending moments that develop deeper than 10 times pile diameter, you only need to apply kinematic loads. You don't need to combine them with inertia. Those are typically the bending moments that develop at the bottom of the liquefiable layer, and they're unaffected by inertia. For these cases in the middle, that the bending moment develops at what we call a shallow depth from ground surface down to 10 times pile diameter, then you are dealing with two cases. If you have cases that resemble profile B1 shown on the left side, these are cases where you have deep-seated liquefaction underlying a significant non-liquefiable crust. In these cases, you need to combine 100% of kinematic with somewhere between 30 to 60% of inertial load. In cases where your profile looks more like a profile B2 here, you need to combine 100% of kinematic with 90 to 100% of inertia. And these are cases where you have shallower liquefiable soil with a thinner non-liquefiable crust. The other thing that I want to mention is that when we talk about the combination of inertia and kinematic, we need to also talk about how to estimate the kinematic load. And there is a huge uncertainty in how to estimate those loads, the lateral spreading loads. Force space approaches are commonly used as a kind of a more simple design methodology. And those force space approaches usually assume that you're applying a uniformly downslope passive pressure on the piles. What I want to show you is the results that we back calculated from these centrifuge tests. So what you see here is the soil reaction profile along the pile at a time when the inertia was maximum in the downslope direction. So these are P in a PY curve, similar concept. When the P or the soil reaction is positive, the soil is pushing upslope. When the soil reaction is negative, the soil is pushing downslope. What you're seeing here is the result from two different gram motions for this test, and both gram motions are essentially telling us the same story. The fact that there's no uniformly downslope soil reaction at the time when you have maximum inertia. There are parts of the crust that is applying upslope, they're in fact resisting the inertial load, and there are parts of the pile where the crust is pushing downslope. So if you choose to use a force space approach for these cases, you will be massively overestimating the the lateral spreading force. This is particularly the case when you're dealing with more relatively flexible piles, where the pile kind of follows the soil deformation pattern. So for these cases, our recommended approach is to use displacement-based approach, where you say, like, if you're using L pile, you would apply the soil displacements to the end node of PY springs, and you capture a more realistic behavior, more realistic soil reaction on your piles. Now, how do we get those soil displacements? Caltrans has a nicely described document on how to use Newmark sliding block analysis to get the pile restrained soil displacement. This accounts for the restraining effect of the piles, or it also sometimes called the pile pinning effects. You need to kind of combine the analysis. It uses lateral pile analysis in software like LPile, combined with limit equilibrium analysis in something like slope W. What we wanted to check was whether, if the displacements that we estimate using Newmark block analysis resemble or estimate the peak displacements or the permanent displacements. What you see in blue is the displacements recorded in the centrifuge test. At the peak transient displacement is somewhere around 0.13 meters, but the permanent displacements are smaller. They're about 0.1 meter displacement. What we found is that let me go back. What we found is that the median Newmark displacements, when you look at the accelerations within the liquefied mass, the median values reasonably estimate the permanent displacements, but they underestimate the maximum transient displacements. However, in design, there are sometimes factors that underestimate the displacement, but there's some factors that may overestimate it. And this is one of those cases where you have two factors canceling, two issues canceling each other's effect. The soil, what you see here is with red is the soil displacement profile, the idealized soil displacement profile, where you get sharp transitions at layer boundaries. The displacement recorded in centrifuge does not have those sharp transitions, and it's more has more curvature to it. If you use the median displacements, even from Newmark displacement, even though you're underestimating the maximum transient displacement at the ground surface, because of those sharp transitions at layer boundaries, you'll be overestimating the curvature in the pile or the bending moments. So when you look at the estimated displacements from L pile versus measured displacements in blue from centrifuge, you're actually estimating the peak bending moments pretty reasonably well. So our recommended design was to use the median Newmark displacements with the idealized soil displacement profile that you would do in your design. So in conclusion, in conclusion, the inertia and kinematic factors could range somewhere between 30 to 60% if you have deep-seated liquefaction, or could be higher, 90% to 100% if you have a shallow liquefiable soil. Bending moments adjacent to pile head can be reasonably estimated by only applying the inertial load. Bending moments at deeper locations, deeper than 10 times pile diameters, can be reasonably estimated by applying kinematic loads only. The load combination factors are about 15% increase when you're dealing with subduction earthquakes compared to shallow crustal faults, which is similar to the approach that the Washington DOT adopts. There's quite a bit of range in the inertial multipliers. So if that uncertainty has significant effect on your project, using an approach like what Port of Anchorage suggests seems reasonable, using a peer-reviewed 2D nonlinear dynamic analysis. These methods are more appropriate for pseudostatic analysis and not appropriate when you have simplified equivalent fluid pressure. And we also recommend using Newmark type analysis with idealized soil profile to estimate the bending moments. And with that, thank you, and I'll turn it back to John for the next presentation.
Thank you, Arash. We're gonna do a little switch over to the slideshow for our next presenter. Bear with us, but Dr. Motamed will be starting up in just a second.
Okay, thank you for the opportunity to present at DFI's webinar series. I'm going to present on some recent experimental work we've done at UNR, and my main focus today going to be on the performance of helical piles in mitigating liquefaction-induced shallow foundation settlements using shaking table testing. I would like to start with acknowledging my hardworking current and former graduate students. Their names are listed at the bottom of this slide, who produce all the work and all the data I'm presenting today. I also would like to acknowledge our sponsors, PEER, Ramjack, and DFI, and also our collaborators at UCSD, as well as Professor Serrato at University of Oklahoma. So in my presentation today, I'll start with a quick background and motivation. Then I'll move on to describing our testing program. I spend more time on our mitigation test series, in which we utilize helical piles, some example results and key observations, and some concluding remarks at the end. And then I'll wrap up my presentation with some of more recent ongoing tests at UNR. This is a photo from the recent earthquake in Japan, the Tohoku earthquake, magnitude 9. You can see a building, multi-story building on the left of the photo, sitting on pile foundations, did not suffer from any settlement as a result of extensive liquefaction in that area, whereas surrounding ground settled about 12 inches as a result of widespread liquefaction. But the interesting part is this building, lowest story building on the right, sitting on a mat foundation, which settled over 27 inches. So this form of damage was widespread as a result of that earthquake in 2011. The reports suggest over 27,000 buildings suffering similar damage. We observe very similar also pattern for damage in buildings and in earthquakes in Christchurch, New Zealand. Overall, buildings sitting on deep foundations, they perform well in liquefied zones, whereas buildings sitting on shallow foundations, they observed significant damage. And I wanted you to remember those settlement values, you know, the ground settling about 12 inches versus building settling exceeding 27 inches. And there's, you know, a factor greater than 2 when comparing those numbers. This is another example from 1994 Northeast earthquake, showing the overall property damage and the portion attributed to the residential buildings. You see that even though damage to a single residential building may not be significant, but once you add thousands of those buildings, the overall damage becomes significant. This is another example from 1989 Loma Prieta earthquakes in the Bay Area, and the building, 3-story building, was damaged, and liquefaction played a key role causing that damage. Some other examples from 1999 Kocaeli earthquakes in Turkey, tilting and sinking of buildings into the ground as a result of extensive liquefaction, loss of bearing capacity as a result, and you know, again, very similar stories in even recent earthquakes in Turkey this year. Based on extensive field observations, followed by centrifuge test. Professor Bray at Berkeley, he has proposed 3 control mechanisms of this phenomenon. The first one is ejecta-induced. Second one is shear induced, and third one is volumetric induced. And those 3 mechanisms, they contribute to the observed damage in buildings sitting on shallow foundations in liquefied zones. And I'm highlighting the first mechanism, ejecta-induced, because I'm going to refer to it throughout my presentation in multiple occasions. The topic of buildings on shallow foundation in liquefied zones has been well studied by different researchers using different approaches. Really, the first documented or the first published paper in this area by Yoshimi and Tokimatsu in 1977, based on field observation from 1964 earthquake in Japan in Niigata. Followed by some 1G shaking table testings. A lot of work has been done already using centrifuge tests in this area, as well as 1G shaking table tests and also numerical modeling. So having acknowledged all the great work done by researchers in this area, my presentation is focused on using 1G shaking table testings at multiple scales on this topic, and that's simply because of availability of testing facility at UNR. So this slide shows a wide range of different soil boxes and used in 1G shaking table testing. You see from top right, the largest one is E-Defense in Japan. It is the height is exceeding 16 feet. To the next one is a laminar box at the UCSD. The height is about 15 feet. And then to UNR is a recently completed soil box, 15 feet in height. And then to another one at UCSD, 9.5 feet. And then at the very bottom is again another UNR box, 2.6 feet in height. So having these wide range of testing facility and soil boxes to build models. Obviously, we would like to build our model as large as possible to make it possible to make our models, prototype or very close to full scale. But then there is a drawback with the cost. You see this picture of, schematically showing that as you go to larger scales, the dollar amounts increasing drastically, and the drawback is the number of tests the PIs or researchers have an option to do. So keep that in mind. So for the purpose of our test, the first part of my presentation is used. We use the 9.5 feet in height of a soil box at UCSD. Past several years at UNR, our research has focused on studying liquefaction-induced ground movement effects on residential buildings, low-story buildings, and also more recent years, we are focused on studying mitigation measures. Not every mitigation measure, we are focused on using cost-effective measures. And as a part of that study, we've used helical piles, which is the main focus of this study, but we've done other measures such as lowering groundwater table, installing sheet piles, and all of that, which I'll briefly talk about that toward the end of my presentation. So as a part of our testing program, we carried out 2 series of larger scale tests. The first one, which I'm going to refer to as a baseline test, was done in June 2018. No mitigation measures. The intention was to reproduce the damage and mechanism. And then for the second test done in April 2019, we utilized helical piles as a countermeasure, and I'm going to refer to that test as a mitigation test. Each testing featured multiple shakings, including white noises, to characterize our model. You see the PGAs of the testings of input motions, all greater than 0.5 G. This is an example of achieved input motion, which is basically recorded acceleration at the table. This is a laminar box at UCSD we utilized. The height was about 9.5 feet. And these different layers, they can move relative to each other, reproducing free field ground conditions and minimizing the boundary effects. Our model included shallow foundations, rigid shallow foundations, sitting in the middle on a 3-layer soil profile. Groundwater table was at depth of 2 feet. We placed weights on top of the footing to reproduce equivalent to a 2-story building. Contact pressure was in the order of about 868 PSF, and then the model was extensively instrumented, using different sensors, not shown on this picture for simplicity. And then we had a cross at the shallow depth. In the middle, we had a 4 feet thick loose sand, and at the bottom we had a 3 feet dense sand. So this was our first test. In the second test, we kept everything the same except installing 4 helical piles. So one may question, how realistic that tall laminar soil box is. This is an example from Christchurch earthquake that one building suffered significant liquefaction-induced damage, and it was well studied, well characterized using in-situ testings, and field observations followed by in-situ testing suggested a 8-foot thick liquefiable layer toward one corner of building, causing damage. And that again, this is the picture of that building, and again, very comparable number to my previous slide, 11 inches of settlement caused by liquefaction. So that box is studying shallow liquefiable soils. It's a very good fit to use for that purpose. For all the helical piles were extensively instrumented using strain gauges. It was a very tedious, elaborate work to make it, to do it right, to avoid any damage or loss of data as a part of the test. We use a bracket connection to connect the piles to the foundation. And that was another challenge, because the design did not include it for seismic design. So we had to make some assumptions and do some in-house design for that. And I think the big question was how suitable for dynamic loading going to be. And I think at the end of the testing, we were able to answer that question. Some more pictures of the piles being before instrumentation on the right, in the middle of instrumentation. We went through, just for the sake of time, I'm not going to explain. We went through multiple different phases of installation, protection to avoid damage, shown here, which I think saved us, a lot of time at the end. We did not have any major issues with losing data. Some more pictures of how the helical piles were attached to the foundation. This is a model of the footing with all the weights on the top to reproduce that contact pressure. This is the top view of the model. We had, as I mentioned, we had extensive instrumentations using different types of sensors, accelerometers, different formats of accelerometers, pore water pressure transducers, string pots, linear pots, as well as strain gauges. So overall, about 150 channel of data. This is how pairs of strain gauges were attached to the piles, and also multiple arrays of sensors installed around the foundations to capture the free field soil response. We characterize our model using cone penetration testing. You see the CPT setup before, during measurements. So we repeated the CPT before shaking, before every shaking sequence, and also at the very end of the testing. So the first video is a specific camera. We had multiple cameras. I picked only this one for the sake of time. This shows how the foundation and footing behaved during the baseline test, in which there was no helical piles. So model was shaken, then the foundation started to rock and tilt, as well as sinking into the ground. And even when the shaking is stopped, the settlement continued. The second video from same angle, this time it was for the second test, in which the foundation was supported on helical piles, and you can see that the shaking happens, what happens to the footing, and all of that. So now you can see the action, and during shaking, once shaking is stopped, sand ejecta, you can see the sand ejecta here coming out of the ground. So this is a model before test, after test. Visually speaking, by observing these pictures, you can tell that there was no damage or significant deformations, whereas in the baseline test, we had a significant settlement. So these pictures showing the baseline test before and after the shaking. This is a picture of that surface manifestation or sand ejecta that you saw in the video as well. And it was very important for us to see and clearly show that we were able to reproduce that, because if you recall, one of the controlling mechanisms of this phenomenon is sand ejecta. And this was especially very important for us because some of the previous experimental work in this area, they were not able to reproduce sand ejecta, but we have proven multiple scales that we can easily reproduce the sand ejecta. These are the helical piles extracted after the testing, and we carefully inspected them, making sure that there is no damage or plastic deformation. So overall, they perform very well. And among a whole bunch of data and results, for the sake of time, I picked this results to present. What you are looking at are two settlement data versus time. The blue one is the baseline test. You see that during the shaking, this period duration, we had a drastic settlement, and when the shaking is stopped, even the settlement continued. During shaking attributed to one of the mechanisms, shear induced, but post shaking there were volumetric induced and ejecta induced, as you saw in the video. Whereas during the helical pile tests, we had a settlement only during shaking, and after shaking there was none of other factors. Although these two may look familiar, may look very similar, but we are using different axes to present them, because they are, in terms of magnitude, they are drastically different. The blue curve reached about 11 inches of settlement. Again, I've kept repeating 11 inches of settlement for a few times now. So even in our testing, very consistent with the field observations, whereas the blue curve only reached to 0.5 inches of settlement, which was very acceptable and satisfactory. So some of the key observations: overall helical piles performed very well. They did not suffer any damage. We were able to reproduce sand ejecta in our test, which was really key. This large scale testing on this phenomenon is really one of the first of its kind. So some great opportunities. I'm going to talk briefly about that in a bit. Industry support for our test was extremely important, so I want to repeat appreciation to Ramjack for their help. And as I mentioned, this was collaborative project, UNR, UCSD, and Ramjack, which brought some unique aspects to our testing, some unique capabilities. At the same time, coordination was key. This is a picture at the end of the testing, helical pile testing. You see some our friends at Ramjack. Ramjack did produce a really nice video you can find on their YouTube channel. Just for the sake of time, I'm not going to show it, but highly recommended you look at it. So for the sake of time, I only presented very limited data, but I wanted to mention that the baseline test results are well presented in a paper in ASC on the left, and the mitigation test results are, again, well presented and documented in another paper in Soil Dynamics Earthquake Engineering. So anyone interested reading those papers, look at all the results, feel free to reach out to me. I'll be happy to share the papers. So I want to quickly go back to the size versus cost chart I had. So we had given the budget restrictions, we only did 2 tests, larger scale, but we wanted to explore, do parametric study, look at the effects of different parameters such as ground motion characteristics, soil profile characteristics, effects of inertial forces in terms of different superstructure weights. So we ended up utilizing the smaller scaled soil box at UNR. You see some of the testing illustrations here. For example, we wanted to look at the number of helices on the response of helical piles. And we look at different parameters. And here is an example results of how those parametric study results turned out. This is showing number of helices versus reduction in the maximum moment. As you would expect, but increased number of helices, maximum moment was reduced. Again, careful and detailed description of the results, and all documented in a paper in DFI journal. And feel free to check it out on the DFI journal website. At the same time, we also wanted to take the advantage of that larger scale test. So we built a 5th model of that larger scale test at UNR. We validated basically the test setup was identical, just a 5th scale. Again, you see, for example, here we use weights on top of the footing to mimic the same contact pressure scaled. So we have a validated model that we could use to do further parametric study. And this is a video of that scaled version of that larger scale test. You saw the video. So you see the rigid footing here, multiple instrumentations throughout, and then you see now the shaking and sinking and rocking of the footing into that layer. The ground profile was also very comparable. So using this new or validated scaled model, we utilized other mitigation measures. Some of the results will be presented at DFI 48 this year in Seattle, and some of other results will be presented at Geo Congress next year in Vancouver, Canada. So that was my last slide. Back to you, Kevin and John.
Thank you, Ramin. Much appreciated. I think with that, we can go into the Q&A session. We have right now a couple of posted questions to the first presentation. The first one, I'll read them out and let Dr. Khosravifar answer each one. The first question, to clarify, with the recommended kinematic demand contributions, the kinematic values are coming from the individual depth PY spring, in other words, displacement based, and not the driving wedge estimated from Caltrans 20-15 memo to designers, in other words, somewhat force based.
Yeah, that's correct. So we have, there are displacement-based approaches where you apply the soil displacements to the end node of PY springs, and that's easily done in software programs like LPILE. And then there are force-based approaches where you estimate the lateral spreading force based on the passive pressure on pile. And there are various recommendations from Washington DOT, Caltrans, the Japanese design guidelines, which again, they use some variation of those passive forces along the pile within the non-liquefiable crust. We can't really discuss the inertia and kinematic factors without discussing the uncertainty in estimating the lateral spreading force. And this is pretty important. If you're especially if you're dealing with more flexible piles configured in a large pile group, such as the centrifuge test that I showed you, and you estimate your lateral spreading displacements using full passive pressure on piles, you're likely overestimating demand significantly. So if you're overestimating demand on lateral spreading force, on kinematic force, it would be over conservative to combine those demands with the inertial load that we discussed. So the inertial load combination factors that I presented are suited for a case where you're estimating your kinematic load using displacement-based approaches.
Okay, thank you. Hopefully that answered the question. The second one is, do you have any guidance on the inertial factors when considering an enclosed building supported at grade founded on piles as compared to bridge bents or wharves supported some distance above grade?
Yeah, that's a very good question. Most of the research done on this topic has been from either highway, bridge agencies, or wharf and ports. To my knowledge, there hasn't been a research on specifically the combination of inertia and kinematic for buildings supported on piles. Having said that, as a lot of you are aware, ASC 716 for the first time included some provisions on settlement limits and lateral spreading limits for the use of shallow foundations. But it was kind of a baby step. So they included those for the first time in 2016, but there was no recommendation on whether if you have to combine the two loads when you have pile supported buildings or you shouldn't combine them. I've been told that the NIHER provisions update committee, they're working on including some language in the next provision that will be released sometime in the next year or two on this combination factors between inertia and kinematic specifically for buildings, which I assume that will then get adopted in the next cycle of ASC 7. Having said that, the closest guidelines that I think comes close to the type of configurations that we have for buildings is the 2011 peer report. That's the Ashford et al. 2011. And within that report, they provide the load combination factors for superstructure, so like a bridge deck type of structure, as well as the pile cap. And I think the load combination factors that they provide for pile cap are probably closest to the building supported at grade level that John is asking in his question. So that would be my recommendation to use in the absence of any kind of solid guidelines from NIHER or ASC 7.
Okay, very good. Thank you. We just had one question come in for Dr. Motamed. It said, years ago, we conducted centrifuge modeling to simulate seismic behavior of micropile systems. The biggest challenge we had was always the control of boundary condition effects and the interface conditions at the soil pile interface. How did you deal with this issue?
Good question. About the model boundary effects, we took different measures how to minimize it. For larger scale testing, it was a laminar box, which is meant to minimize the boundary effects because basically the ground can move, freely with minimum restrictions from the box itself. And the model was built in the middle of the box. And we placed enough spacing sidewise compared to the size of the box. In terms of our scale testing, even though our soil box was rigid, we had a relatively long soil box, and we placed our model in the middle as far as possible from the boundary. We placed some special foams on two ends to, again, reduce the wave reflections and boundary effects, again, to minimize the boundary effects. And there has been extensive study, centrifuge tests they've done in the UK, in Cambridge, how to minimize the boundary effects when you have a rigid soil box. And so I think that was a part of question. Another part was the soil pile interface. So people have dealt with this differently. Some have used some glues, and they've glued some sand on along the piles to mimic some friction along the piles. Maybe if you have a macropiles, that becomes more critical. Whereas in our case, really those helices were the main resisting components. So we intentionally, because we wanted to really focus on the performance or the effects of helices to support lateral loads, we did not glue any sand on the shaft part of the helical piles. But I've seen that some people have done that to create some level of friction.
Okay, thank you, Dr. Motamed. Hang on. Yeah, okay. I don't believe we have any additional technical questions. If there are, please type them into the Q&A chat box or raise your hand right now. Otherwise, we're a bit ahead of schedule, but hopefully the two presenters answered any other questions you may have had during their presentations. So I want to thank them again. And not seeing any other questions. So just to follow up, PDH certificates will be available after paid up registrants complete the webinar evaluation through the event module. Access instructions will follow via email. You can always register at dfi.org for other webinars. This series will continue. Our next one will be, I believe, in early December. We're planning to host the second What's Shaking webinar. Please give us your feedback and suggestions. We obviously welcome that. We want to make these as useful to you as possible. Any technical questions, please direct to techactivities@dfi.org. I would like to take this opportunity to myself thank DFI for in part sponsoring the research efforts that went into these webinars that were presented today. And I would certainly encourage every participant to consider, if you're not a member of DFI, obviously to join DFI, but also specifically to join the Seismic and Lateral Loads Technical Committee, where you can keep up and contribute to the latest cutting edge research in this very important field. So don't see any other questions. So I think with that, thank you again, Dr. Khosravifar and Dr. Motamed. Very good presentations today. And I guess we will go ahead and close it out.